Hello. Thanks, Suzanne. And it's really a pleasure to see you all in person and to see that you actually have legs and pants on. So that's really reassuring. So what I want to present here is some work that really great news was actually accepted last night before I got on the plane. So Fabian Fasnacht sent me the OK email. So it's accepted and will be published soon. And it was done within Smart Forest, which is this long-term research program that we have in Norway, and it's still ongoing. So just a bit of branding there. It's not just my work, and it's some colleagues at Nibio that have done this with me also. So the main idea of this was to go from an ordered point cloud, or, well, actually, the idea was to go from a point cloud or single trees, so skipping that cumbersome step of doing the single tree segmentation. We did it manually, a bit of a trick around it, but it was just to kind of look what are the possibilities when we have a perfectly segmented tree. What are the possibilities? What can we do with it? And in our case, we wanted to derive height-age curves for single trees, so what you see, those orange lines, and at stand level. So what is this useful for? This is useful for understanding site productivity, which is ultimately very useful for forest management. So how do we measure height growth in a tree? Maybe it's one of a small detail that we don't look at it very often when we look at these nice point clouds that we have, but we get a lot of information about whorls, and whorls tell us a lot about how a tree has been growing and how it is growing, and perhaps it can help us to understand how it will grow. So that's very useful information, and you can see it at the base of a tree, or you can see it on the treetop. Of course, it gets challenging in some parts of the trees, but what you see here, it's drone laser scanning data. So it's not as nice as TLS, but it's much better than like airborne laser scanning data. So we can get these features, but we can't apply algorithms that have been developed before for TLS. So that's a bit the starting point of the work that we're doing. So we collected drone laser scanning data over these two stands, and we measured about 20 plots. This was spruce-dominated stands, mature, where they were just before the harvest. And there we selected 40 trees, for Norway spruce trees. They were selected in order to cover the range of volume of trees that we had in that area. And that is located just in Oslo. We collected some mini-VUX data over the area, nothing particular. We actually didn't even do it ourselves. We hired someone to do it. That's how the data looks like. Again, nothing automatic in this case. We just manually went there and cut out pieces of the trees and put them together. Then we went in these stands and with harvesters. So now this is bringing us to very operational settings. Was very challenging. This was in January, and suddenly it was like the main snowstorm we had in the year. So it was quite fun, but also quite challenging to run this experiment. You see here, the snow actually had melted, so the harvester had gone in there. We had marked those 40 trees that we wanted to sample. So for those trees, he just like felled them without processing them. And then we went in with the chainsaw and we cut these little stubs so we could actually walk in there, measuring tape from the base of the tree, and we measured the distance between all visible whorls. So we didn't go and split the tree in half. That was too much. So we just assumed that whatever we could see was a whorl. So pretty straightforward. How did we take it from there? So we had this single trees that were manually annotated. a fantastic thing of these point clouds that we have is that we can take and start slicing these trees in any possible directions. So we took the tree, started slicing it. In this case, we took 4 different slices of that tree, produced these 2D projections of those trees. We split those even into different squares. The reason is because then we fed all of this into a convolutional neural network. And the way that works is that it takes square images, and putting a tree into a square image, it distorts a lot and removes a lot of detail. We annotated some of these squares manually. You draw bounding boxes, as you see here, trained this object detector. In this case, we used the YOLO V5, and so forth. We then predicted on the new trees and aggregated those predictions, converted those predictions into height age curves. Just to go a little bit more in detail, we took about 141 images, and we selected these in a way that they would cover a bit the range of situations that this algorithm could see. So we took some at the base of the tree, some on the treetops, and so on. And here we annotated all visible worlds, and in total we had about 1,900 worlds. This is work that took about maybe half a day. So one important take-home message here was that a lot of people are scared to get into deep learning because of the need of millions and millions of data points. Well, that's not necessarily true all the time. You can start small and ramp it up as you go. So in this case, it was not really a whole lot of annotation. We trained this YOLO. In this case, we used this YOLO V5, which is a recently, well, not so recent, but maybe like a couple of years old. But it's just fantastic. It runs like without a glitch. And it's basically what it does is bounding box detection, what you see in like cars and so on. We trained it using our annotation. And this is what we get out of the YOLO as we trained it. Precision and recall of 0.5, 0.4. Okay, not that great. This, however, is basically just on the raw images. So it's not looking at all the slices that we took from the tree. So not great initial first step. However, when we take all these slices that we had from the tree, and we run predictions on all of them, and we aggregate all of those, then suddenly the performance gets much better. And this tells us like really an advantage and a very exciting opportunity that we have with point clouds and deep learning of creating virtually any projection of the data that we have. So we produced 4 slices. We could have produced 100, and perhaps the accuracy would have been even better. But basically, what we do in this post-processing, which is actually a very important step, first of all, we need to bring this kind of image coordinates into a UTM coordinates, and then we need to aggregate and then clean them up. And the cleaning is very easy. There's no fancy, really, algorithm. It just selects overlapping boxes. Here, it selects the one with the highest probability, and so forth. And it does this iteratively until it's done. There's no more overlapping boxes. And so this is basically the outcome, the result. Doesn't look that great, but really we don't really need these boxes at the end. We can get an average between the top and the bottom, or what is it, the X max, Y max, Y min. We get the average, and then we get the word point, because this box is supposed to kind of enclose that point in the middle. So we saw that the accuracy and the precision and recall improved. What was interesting is that the F1 score, which is it measures both precision and recall, it increased going from the base to the top. And all of this resulted in a mean annual increment RMSE of about 8 centimeters with about 5 centimeters of bias. Just another image of how you can visualize this kind of multi-view when you predict from all these different slices and you bring it back to a point cloud. You can kind of plot these points onto the stem. Those are the worlds. So when we predict on all of the trees, in light blue you see what we measured in the field, and in orange you see what we detected from this YOLO. And you can see that it's actually pretty nice. And what we're interested in is really like the slope of those, not really whether they fit perfectly. So you see that for most of the trees it actually went pretty good, and there was no significance based on there was no significant differences in performance based on the size of the trees. So that's also quite encouraging in terms of getting biased results. What happens when we bring this to the stand level? We aggregated all of these trees, so all of those orange lines to the stands, and we see that this is the height age curve that we measured, the blue line, and the world detector, what it gave us is the dashed line. So it's actually pretty nice. You fly one time with the drone laser scanning and you get that kind of level of data. Solving the problem of unknown age for site index estimation, maybe we haven't solved it all, but what's exciting is that we released this also as a GitHub repo, mainly in R, and you can go and test and play yourself with it. And so that's pretty much it. I think, yeah, just this is some future developments, how we bring it also to some other data sources and so on. But yes, so that was all. Thank you.
Very exciting new developments, Stefano. Thank you. There is a question here.
Yeah, very nice work. I was just wondering, do you have a solution for deciduous species?
No, we don't really consider deciduous species in Norway. No, but of course it can be a further development. In this case, we just looked at Norway spruce. Yeah.
May I ask, what is a whorl?
Whorl, it's basically this crown of gems that are produced yearly. So every year there's an apical shoot, and then these lateral shoots, and these lateral shoots create these whorls. And, yeah.
Thank you for the nice presentation. Maybe I missed something, but is there a reason why you use because I understand that you use the 3D, the point cloud, and then you create a 2D projection. Is there a reason why you don't just use the photos instead? For example, if you take photos and then you label them, you should also be able to do the same thing, right? Is there any particular reason why you use the 2D projection of the 3D? So because it means more steps to do it, right?
You mean like from ground-based photos?
Yes,
like,
for example.
Yeah, that would be a very cool further development, exactly, like to take it and perhaps with this pre-trained network and bring it to photos. The reason is just that we had laser scanning point clouds.
All right, well, thank you one more time.